Hello, in this graph, we are going to be learning about the meaning of slopes and areas of graphs. Specifically in this video, you're going to learn about the difference between symbols for quantities and units of measure. We'll be looking at how to use units to determine the meaning of the slope or the area of the graph. We'll be looking at how to create a name and symbol for the slope or area of a graph if it's not a commonly known meaning. And we'll be learning how to create a physics equation of a line from a graph. Let's start with looking at the difference between quantities and units. So in this table, we see a number of different columns. There's a column for quantity, symbol, unit, abbreviation, and subunit. The goal here is to help you distinguish quantities from units. See, quantities are things we might want to measure, like energy, height, force, weight, or mass. Others, of course, time, things like that. Units are the measurement that we're going to use of that particular quantity. For example, energy is commonly measured in joules. Height would be, at least in physics, we'll be commonly measuring it in meters. But of course, you could measure it in feet or inches or miles or anything like that. Force is measured in newtons. Weight is measured in newtons. Mass is measured in kilograms. This is the difference in quantity, the type of thing you want to measure, and the unit specifically how you're going to measure it. Now, frequently we don't want to, especially in an equation, we don't want to write out a whole word. So we have a symbol that represents that quantity. So for example, E represents energy, lowercase h represents height, etc. Similarly, for units, we have an abbreviation, a way to not have to write the whole unit. And the unit for joule is capital J, for meter is small m, for Newton, capital N, etc. It's important to distinguish these two things, first of all, because they're communicating very different things. But second of all, because sometimes the thing looks the same, like here's a lowercase m and here's a lowercase m. So when we are looking at an equation, you will see a lowercase m if the quantity mass is in the equation. You will never see m for meter in an equation. You will see m for meter after a number like 17 meters. So it's important that we distinguish what's a symbol for a quantity and what's an abbreviation for a unit. Now, some units are fundamental, but other units actually consist of a combination of units. For example, a joule is a Newton times a meter. You might think of that as like force times distance, which is sort of like the work equation. A Newton is actually a kilogram meter per second squared. You don't really need to know any of these through this video, but I wanted to make you aware that sometimes units are fundamental and sometimes they're not. I want to speak a little bit about slopes of graphs. Most of you from your math work know that if you have a line, then the slope of that line is a number we can figure out. The sort of the super common thing to think about, or that your math classes teach you, is that slope is rise over run. You may see that as y1 minus y2 minus y1 over x2 minus x1, and many of you know how to do that. I like to think about the slope as how steep the line is. If we imagine being on our line, going for a sled ride down our line or up our line, how steep that is. So steeper slopes will have bigger numbers here. Less steep slopes will have lower numbers, and the line could be, for example, if it's like that, it's a lower slope. Like this is a higher slope. Now, some of you who have had calculus will be aware that slopes apply to curved lines also, but if you haven't had calculus, you might not be aware of that. So let's imagine, again, sliding down our hill. The hill is not very steep here, but if we get our sled to the point where it's here, now the hill is really steep. So we can think about the slope of a line, a slope of a curve, as being like how steep the hill is at that moment. Um, some of you mightn't be aware of the concept or term of tangent. So if we put a dot here, we can say the slope of that line at that dot is how steep a tangent line would be, something like this. And so if we put a dot there and drew a tangent line there, then we could actually, maybe like, from math class, we could go figure out the rise by looking at the two y points. Something like that, and we could figure out the run here. So we could figure out the rise and the run and figure out the slope of that line, even though it's really just at a point. But again, every curve has a slope at a different slope at different points along the curve. So that's a little bit about slopes of graphs, particularly when it comes to curve graphs. It's going to be something we'll be looking at a lot in physics. And I want you to have at least some sense of what we would mean by the slope of a curved graph and how that slope changes. Now let's specifically getting into the idea of what is the meaning of slopes and areas of graphs. So this was an example off the pretest. We make some popcorn pop in the microwave, and it starts out popping like pop, 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 but slowly but surely becomes like pop, 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 pop. And of course, if you popped all the kernels, then you hear no more popping. So what would the graph of the number of kernels popped, what would that look like? Well, eventually you're not going to pop anymore. So it can't be a line that goes up forever. In fact, it sort of has to level off. So maybe something like this. We pop a lot of kernels really rapidly, but later on we don't pop so many, and then it eventually levels off because we're not going to pop anymore once all the kernels are popped. So this is what the graph would look like. Now, I want us to think, the main thing I want us to think about here is what is the meaning of the slope of this graph? So let's just imagine like looking at two spots here and maybe here. And one of the best ways to think about the slope of a graph is to do kind of an analysis of the units. So time, let's measure this to be in seconds. And so a number of kernels popped is just a number without really units. So the slope is the rise over the run. Let's see what that looks like with units. The rise is in like number of kernels, and then the run is in seconds. So the units of the slope are kernels per second. Kernels per second. Now, that might not be like miles per hour, most of you would know is speed. This might not be a commonly acknowledged quantity, but it is kind of meaningful, like kernels per second. That's sort of telling us the rate at which the popcorn is popping. So it is a meaningful quantity, rate of popping. And so that's really what the slope is telling us here is the rate of popping. Now, this isn't a line, but if it was a line and we wanted to, say, make an equation of that line, we might have to decide so in general, y equals mx plus b, but this is not generic math. We have very particular quantities here. And so the y-axis is the number of kernels, so why don't we use the letter k to represent the number of kernels? And then the x-axis is time. Let's use t. That seems pretty obvious for that. Um, this will be like the beginning number of popped kernels, which is 0. And now in here, we will put the slope, which we could put the number of the slope, but maybe it's different for different brands of popcorn. So let's make up a symbol for the rate of popping. Let's make up a symbol. Let's sort of use the paragraph uh, symbol that you might recognize for English class. Why? I don't know. I get to make up a symbol because this is not like a super well recognized quantity. So I'm going to make up my own symbol for it. And then here's my equation for that line in symbols that will make sense for this context. So what I've done so far is I've talked you through how to use units to figure out the meaning of the slope. Like, what is it telling us? We can see the slope is very high here and lower here, which means the popping rate is higher here and lower here, which is probably what you would have said. And then I've also developed an equation in good symbols and symbols that are meaningful, symbols like K, this paragraph thing, T, symbols that are meaningful for this context. Now let's go over and do this other graph, which was also on the pretest, the speed or rate of kernels popping. Well, that was this thing here. And you can see the slope starts out pretty high but ends lower. So this graph has to start out high and end lower. So let's just say it does something like this. We won't worry too much about exactly, but somehow if it starts high and gets lower. So that does that. Now, in this case, I want to ask the question, what does the area of the graph tell us? So what I mean by area is this thing right here, which is like a triangular area. It's whatever's between the x and y axis and the graph line. It's that area there. So some of you recognize that as a triangle, I hope. Area is 1/2 base times height for a triangle. Let's again use unit analysis to figure out what the area might be telling us. So half doesn't have any units, but the base is in seconds. And the height is the popping rate, which we said over here was number of kernels per second. And if we multiply those units together, as many of you know from math class, something on the top and the bottom fraction cancels out. So we're really left with number of kernels. And that means the area of the graph tells us how many kernels have popped. If we do the whole graph, it would be the number of kernels in the bag. But if we did for just like part of the time, like half of the time, then this area in here would tell us how much of the how many kernels have popped in total up to that point in time. So once again, by looking at units, we can try to infer the meaning of, well, in this case, the area. Now let's look at a couple of other situations. So here's a situation. I'm going to do a brain experiment. I'm going to pretend I have a special meter that I can put on these two rocks. This is a big, heavy rock and a small rock. And I'm going to pretend I can put a little energy meter on here. And then I'm going to lift it up to different heights like this. And I'm going to measure how much energy is stored in that rock. And I can do the same thing with the smaller rock. Again, lift it up to different heights, and at each different height, measure the energy. All right, well, if I look at the big rock, let's actually make that red and the small rock green. If I look at the big rock and look at its energy versus height graph, it's going to look something like this. The small rock's energy height graph is going to look like this. So again, in examining these graphs, one thing we might want to do is to figure out what is the slope of that graph telling us. So we can, by looking at the graph, we can see that the slope of the red graph is bigger. So it almost certainly, the slope of the graph is related to the weight of these objects here, somehow related. because the red we know weighs more. We did the lifting, and the green weighs less because, again, we lifted that in doing the experiment, and we can see bigger slope and lesser slope. Let's use units to figure out exactly what that might mean. So again, I'm going to go and write out slope is rise over run. And the rise is in joules, and the run is in meters. So joules per meter. Now that itself doesn't seem like a particularly meaningful quantity, but we're suspicious because that it might have some meaning because, again, the lines sort of correspond to the weight, the steepness of the graph. So I'm going to come back to this table that I made before, showed you in the earlier part of the video. And I want us to look at energy. Joules is newtons per meter is another way to write joules. And if we break that down to newtons per meter, Newton meters per meter, now our units actually, because the meters cross out, the units on the slope are actually newtons if we break joules down to its more fundamental components. And newtons is a unit of weight. So in fact, our suspicion that this has to do with weight is correct. The slope here of this graph is actually telling us the weight, specifically the weight. And so if we, for example, did this experiment and didn't know the weights of these things, we could plot the graph. We could take our energy measurements and our height measurements. We could plot the graph. We could figure out the slope, and the slope would tell us what the weight of the object is. That would be a way we could figure that out. So here's a case where looking carefully at the slope gives us the meaning of the slope, which is actually a well-known quantity. Now we could again make up an equation for the line of this graph. I'm going to erase that stuff there. And let's take a look at doing that. So in general, for a line, y equals mx plus b, those symbols have absolutely no physical meaning whatsoever. And in the equation we want to write in physics, we want the symbols to help communicate what the graph is about. So using x's and y's and m's and b's doesn't make any sense. It doesn't tell us what the scenario is. On the other hand, certainly if we look at the y-axis, energy stored positionally, that's a symbol that we all know what that means. So when we look at this, we will see EP. We will know this is an equation about the energy stored positionally. Now the slope is the meaning of the slope is the weight, and while we haven't been introduced to this yet, the physics symbol for weight is a capital W. Again, we should be able to look at that and say, oh, capital W, that means weight. So this is an equation which communicates something about the weight of the object. And then H is a symbol we've been using for the height. And then the B would be the y-intercept, which would be like the initial amount of before we start to lift. But of course, that's 0. And so 0 is there. And so here's an equation for either of those lines. Like this is an equation that relates the positional energy, the weight of the object, and the height of the object. And we could go ahead and use that equation if we wanted to solve some problem. So again, coming back to the purpose here, we're trying to see how we can use units to figure out the meaning of things about graphs, and then also to write equations using good physics symbols to communicate stuff about what the scenario is about. Let's do yet another scenario. In this one, I'm going to imagine that we have a firefighter who's spraying some water out of their hose. And we're going to plot the flow rate in gallons per minute versus time as the firefighter sprays the fire. And we're going to imagine that maybe over time, for some reason, the water doesn't come out. There's not as much water comes out. So maybe the firefighter is wishing they could have a stronger stream of water, but it's not happening over time. So maybe the graph looks like something like this. I guess I could use blue for this water. Let's imagine it's something like this. So we have our firefighter, some water's coming out of the hose. Maybe the water pressure is dropping, so uh, the flow rate's dropping, and that drops over time. We don't know why, but let's say that's what happens in this scenario. And let's take a look at what the area of this graph tells us. Well, it's a trapezoid, which is like one half, sort of one side. Let's say height 1 plus height 2, and then multiplied by the base. But again, we're not really interested in the specific formula at this moment. What we are interested in is in the units, because the units are going to help us to see what the meaning is. So that doesn't have units. Heights are in meters. Let's say, height is in gallons per minute. The height of the graph, gallons per minute. And then the base is in minutes. Okay, gallons per minute on this axis, minutes there. And by math again, top and bottom of the fraction drop out. So this is in gallons. So what does it tell us? It tells us that this area in here, whatever formula we use to calculate that, is measuring the amount of gallons of water that have come out of the hose. So, for example, if we knew this graph and if we saw this graph, or say for a given fire that was being fought, this is what the graph looks like, we could then say, hey, here's how much gallons of water was used by figuring out the area of that. All right, so going back to the beginning of the video here, we wanted to look at the difference between symbols and quantities, for quantities and units of measure. So we did that early on in the video. We wanted to look at how to use units to determine the meaning of slopes or areas. We did that. We wanted to see how to create a name and a symbol for the slope or area if it's not commonly known. And then we wanted to look at how to create an equation of a physics equation from a line of a graph. And so we've looked at all of those things. And now it's your turn to try this on your own in the associated assignment.